Hi there, my name's Aaron Lanterman. In the last lecture of GPU programming for video games, we started to take a look at Unity's standard shader for its built-in pipeline. I took the shader code downloaded from Unity's website, copied it over to a blank Unity project, where I also loaded in a simple asset in order to have something to test with. And basically what I did is I took all of the files and changed them to have the word my in front, and then changed the references in the files themselves. So, starting with the standard shader, we discovered that there were 9 shaders in it. Only 5 of them were really of value to us. The remaining 4 are variations of it for simpler GPUs. So, these main ones that we're looking at target shader model 3. So the ones we're going to start looking at are this base shader that corresponds to UnityStandardCoreForward and the add shader that corresponds to UnityStandardCoreForward. So in the base pass, it basically handles the main direct light, emissive effects, and light maps. Whereas the remaining lights, whether they're directional or point lights or spotter or whatever, are handled individually in different add stages. So UnityStandardCoreForward basically doesn't do very much. It basically passes things along to a simple version of the shader or the more regular version of the shader. And so we're going to be looking for vertForwardBase, vertForwardAdd, fragForwardBaseInternal, and fragForwardAddInternal in this Unity Standard Core. As I mentioned in the last lecture, this set of lectures is more improvisational than most of my other lectures where I have a lot of things planned out ahead of time. Most of what I'm talking about here, I'll be discovering as I talk about it. So let's first see what's up with the input structure VertexInput. I found VertexInput in a file called UnityStandardInput. It was pretty near the top here. Here we go. So VertexInput has vertex positions, normals, texture coordinates for 0, 1, 2, and tangents. Apparently there's a tangent to world defined in here somewhere. And I should note that when things are compiled, I think if you don't use something, it's not included in the code. So it doesn't hurt to have stuff here that you don't use. So let's go to Unity Standard Core and look for the functions vertForwardBase and vertForwardAdd to see what it does with that vertex input. Okay, so vertForwardBase is going to produce a vertex output forward base. Let's see what that structure looks like. Fortunately, the structure is right above it. All right, so there's a macro. Great. Unity position. Then there's some lighting chords. That's another macro. Oh boy, I don't want to track all of that down. You can go look for that if you want to. Let's see. We also have texture coordinate, I-vector stored in a texture coordinate, tangent to world, and packed data. Okay. So there's a whole bunch of stuff in there. And let's see, what are they putting in texture coordinate 5? Ambient or light map UV. Okay, so this is somehow holding information about spherical harmonics or light maps. And then there's a couple more macros here. Unity Vertex Input Instance ID, Unity Vertex Output Stereo. Okay, so what I want to do is I want to just kind of get an overall feel for things. You can search through the code and try to figure out what these various macros do if you want. And I might do that if at some point I want over the course of this lecture. Or maybe I shouldn't call this a lecture. Maybe I should call it a meandering, a guided meandering. Anyway, let's meander together. Okay, so we're computing a position in the world space by multiplying our vertices by this Unity object-to-world matrix. There's something about this tangent to world and packed data that I don't feel like trying to figure out. This O dot position is equal to UnityObjectToClipPos. So let's look this up and make sure we know what it does. Here's UnityObjectToClipPos. And there's something about stereo cube maps. Not sure what's going on there. Does that have something to do with, I don't know, maybe virtual reality or something? I see some half stereo separation, whatever that is. All right, the main thing we have here is we're going to take the position, strip off the W, and add in a 1 here. I'll talk about why they're doing that in a second. Multiply by the object to world matrix to get into world coordinates, and multiply by this unity underscore matrix underscore VP to convert it into the view space and then into the projected clip space. And the reason they're doing this is this provides a hint to the compiler that winds up producing more efficient code if you look at the final assembly. Okay, what about the texture coordinates? They're taking the input structure and giving it to this TexCoords function. I could maybe title this video, Georgia Tech Professor Reacts to Extremely Confusing Unity Code. Everything is spread out all over without a whole lot of logic. Okay, TexCoords is in Unity Standard Input. This is where they use that transform underscore tech macro in order to be able to do the tiling. Okay, for the I vector, they're taking the position of the vertex in the world and they're subtracting the position of the camera in the world space. Why are they using this function here and not just saying normalize? Okay, I actually found it defined in the same file, this standard core. So we have skips normalization per vertex and expects normalization to happen per pixel. Okay, so if you're doing things normally, it doesn't actually normalize that vector in the vertex shader, but I assume it's going to use this in the pixel shader and normalize in the pixel shader. But it looks like that's only the case if you're using shader model 3.0 or above. If you're using a shader model less than that, or if you're using some sort of special simple shader setting, then it will normalize it in the vertex shader side, but apparently it won't bother to do any normalization of it in the pixel shader. So that's the thing they're doing to save computation time in the pixel shader, even though it produces results that are wrong, but that's a way to save computation, I guess. So if I was going to use the standard shader here as the basis for my own custom shader, the first thing I would probably do is just strip out all of the code having to do with anything with a shader model less than 3. You don't really need any of that in the year 2022. Okay, the next thing we do is we take the input normal that's in the object space and we want to convert that to world space. Let's look up UnityObjectToWorldNormal. I expected to find that in Unity Shader Utilities because that's where we found UnityObjectToClipPos, but nope, it's not here. So it's actually in UnityCG. There you go. So UnityObjectToWorldNormal, if we set a define that says we're assuming that we're not scaling all of our objects, it's sufficient to transform a direction vector for the normal by just multiplying by the upper 3x3 matrix of the object to world matrix. But if you can't assume uniform scaling, as we saw in a previous lecture, this gets more complicated, and then we can sort of use a trick of the way multiplication works in HLSL to facilitate multiplying by a matrix transpose. So this is all pretty complicated. This is something we talked about in a previous lecture, so I won't belabor it here. Next, there's a whole bunch of stuff about tangents that I'm not going to try to figure out. All right, let's keep going. Yeah, I'm giving up on that part. All right, next thing we have is Unity Transfer Lighting. We need this for shadow receiving. I'm going to give up on this part too. You can go look this up if you want. All right, what about this ambient or light map UV? Okay, that's coming from this VertexGIForward. So what is that about? Okay, so here's VertexGIForward. It is in the same file, this Unity standard core, and this is going to get complicated. So it's going to return ambient or light map UV, and that's pretty much what it says on the tin. What's confusing is that this represents two very different kinds of information. If you have a light map for this particular object that you're rendering, then ambient or light map UV contains texture coordinates looking into that light map. But if it isn't doing that, then it does this business of this ambient stuff, And here it's actually returning a color. Now, to talk about what's happening here, I have to talk a little bit more than I wanted to talk about the specifics of how the built-in pipeline interprets lights. So let's check out this documentation on the forward rendering path. Now, you're going to see some references to spherical harmonics. The spherical harmonics discussed on this page aren't the same as the spherical harmonics that we talked about in the lecture on light probes. Well, they are the same in terms of they're the same mathematical concept, but the light probes are handled separately. All right, so in forward rendering, some number of the brightest lights that affect each object are rendered in fully per pixel lit mode. Then up to 4 point lights are calculated per vertex. The other lights are computed as spherical harmonics, which is much faster but is only an approximation. Whether a light will be a per pixel light or not is dependent on this. Lights that have the render mode to set to not important are always per vertex or spherical harmonic. Brightest directional light is always per pixel. Lights that have the render mode set to important are always per pixel. If the above results in fewer lights than current pixel light count quality setting, then more lights are rendered per pixel in order of decreasing brightness. Rendering of each object happens as follows. Base pass supplies 1 per pixel directional light and all per vertex spherical harmonic lights. Other per pixel lights are rendered in additional passes, 1 for each light. And then it gives this nice little graphic here talking about it. The shade 4-point lights routine is actually in UnityCG, and it pretty much does all the stuff you expect. The way it's written is a little weird because of the way the data is packed, but it does all of your usual diffuse computations. So there's also this ShadeSHPerVertex function, which is not in UnityCG, because Unity apparently delights in being completely inconsistent as to where they put their code. Actually, wait a minute. I'm not sure what I said about this just including various unimportant lights in these spherical harmonics is correct, because it says here sample light probe for dynamic objects. So when it says sample light probe, that suggests that it is the actual light probes. So I'm not sure. I think we'll have to dig a bit deeper to figure that out. Okay, ShadeSHPerVertex, that's in the Unity standard utils. Oh, and this is interesting. It looks like if we are saying that we are handling the spherical harmonics on a per pixel basis, we don't actually do anything here in the vertex shader. And then there's other variations that involve this shade SH9 or this SH eval linear L2 that does some spherical harmonic stuff. You can go look these up. I think these are in the UnityCG. Let's see. Shade SH9. There it's computing a bunch of spherical harmonic stuff. Actually, it's calling something else. Let's look up SHEVAL linear L2. All right, here we go. There we're actually computing some spherical harmonics. And to be straight up, I'm not sure I'm entirely following the logic of the code here. Parallax is a really cool effect, but it's not one that I've covered in this class, and I'm not planning on covering it, so I won't talk about that now. Let's see, the last thing we do here is Unity Transfer Fog combined with I vector. All right. And that's defined in UnityCG. So it looks like there's some fog information that's stored in some Z component of something or the other, and that gets stuck into the W component of the I vector with the XYZ containing the actual I vector. Something like that. Okay, so that's what happens in the vertex shader for the base pass, although, truth be told, I probably skipped more than I actually covered. Let's see what's different for the additive pass. So let's look up vertForwardAdd. All right, so a lot of similar stuff. Actually, this looks like a subset of the base pass. Basically, it has all the same stuff, except it doesn't have that ambient computation with the spherical harmonics and the 4 per vertex lights. Okay, so that was all about the vertex shaders. Let's look at the pixel shaders. We want to look at fragForwardBaseInternal and fragForwardAddInternal in Unity Standard Core. Okay, so here's fragForwardBaseInternal. There's some macros that set up some stuff. We have something called the MainLight, and that is a structure Unity light. So let's check that out. Okay, so whatever a Unity light is, it will have a color that it's getting from our underscore light color 0.RGB, and it has a direction. And remember that for directional lights, the world space light position isn't actually the position, it's actually the direction vector of the light. That's just one of Unity's conventions. And then we have this macro Unity underscore light underscore attenuation. Oh, I don't see attenuation defined earlier, so it probably assigns this in the macro. And that Unity light attenuation macro is apparently in this auto light library. All right, so we have a destination, so that attend variable was being written, some input and some world position. All right, so we wind up doing some transformations with the world to light matrix. So this is converting coordinate systems associated with the light, and there's stuff in here having to do with shadows that I'm not going to try to figure out. And let's see, I have this light coordinate dot producted with itself. This looks like it's computing a distance, and then it's doing a texture lookup. What is happening here? Okay, I just did some digging. It turns out Unity is using that underscore light texture 0 business as a lookup table to save computation. Very interesting. Anyway, that gives us an attenuation factor somehow. Let's find this occlusion and this emission function. Here's the occlusion function. It looks like if you're using shader model 3 or above, it looks up the value in the occlusion map, and then it will linearly interpolate between 1 and that occlusion map value based on that occlusion strength slider. But if you're using a shader model that's less than 3, it doesn't include that occlusion strength slider effect. It just returns the raw occlusion map. And incidentally, it's pulling it out of the green, although your occlusion maps are generally grayscale, so they could pull it from anywhere, but just notice it's pulling it out of the green. Oh, I should mention I found this in UnityStandardInput. What about that emission? All right, so it looks like if you're not using emissive textures, you return nothing. If you are using, then you take whatever's in the emission map, but you also multiply it by a color that you might set in the inspector for tinting. Okay, so the emissive texture just gets added in after everything else. That's not too surprising. Let's check out fragmentGI, which sets this GI variable, and that GI variable is used in this Unity underscore BRDF underscore PBS. And this is the main macro I want to focus on. This is where the real work happens. So it takes this S structure that has a bunch of stuff in it that was set in FragmentSetup. We should probably go back and look at what FragmentSetup is doing. It takes in the occlusion, this ambient or light map UV, attenuation, MainLight. All right, so let's check that out. Wow, there is a lot of stuff here. So we have something called a UnityGI input, and it defines things like the light, the world position, I vector, attenuation. That's probably getting passed on to something else. Something about whether or not we're using light maps. Oh, here we have SpecCube. So we have Unity SpecCube blending. So this is all stuff having to do with reflection probes in some way. Let's see. And if we're using reflections, then we do something with this UnityGlossyEnvironmentSetup, and that calls a bunch of stuff. And then we run UnityGlobalIllumination, or we just run UnityGlobalIllumination without the reflection business. So let's first check out what this glossy environment data setup is doing. So UnityGlossyEnvironmentSetup is in Unity image-based lighting. We actually do the reflection command in here, and we're also running SmoothnessToPerceptualRoughness. So let's look that up, SmoothnessToPerceptualRoughness. Oh, is that really in another file? Seriously? Okay, so SmoothnessToPerceptualRoughness is in Unity Standard BRDF, and it's just 1 minus smoothness. Great. Like, I understand that it's good programming practice to break your program into a bunch of small functions and give those functions meaningful names, but at some point it gets really hard to track down what's happening, especially when stuff is spread over so many different files. And then we call UnityGlobalIllumination. Oh, wait a minute. These are different signatures. So this one has 1, 2, 3, 4, 5 arguments. Okay, and then that will call this 4-argument version or this 3-argument version. Let's see, here's a 4-argument version. And what does that do? It calls the 1, 2, 3, 4, 5-argument version. Wait, what's going on here? Let's see, UnityGlobalIllumination, UnityGlobalIllumination. Okay, here's a 4-argument UnityGlobalIllumination. So we can't just count arguments, we have to look at the types also. Oh, good grief. Okay, so this is calling UnityGIBase or UnityGI indirect specular to set our specular and stuff. All right, this version of it with these 3 arguments just calls UnityGIBase. So I think these are the main things I need to think about. So what's UnityGIBase and UnityGI underscore indirect specular? Okay, so UnityGIBase is in UnityGlobalIllumination, and here's a bunch of stuff having to do with light maps and shadow masks, which I don't really understand that much anyway. So let's move on. And let's see, if we're sampling spherical harmonics per pixel, then that's happening here in the pixel shader. So we're setting our indirect diffuse there. Something about light maps. Wow, there's a whole lot of stuff here. Okay, so here we're setting indirect diffuse light. Subtract MainLight with real-time attenuation from light map to co-directional light map. All right, here's something about dynamic light maps that we haven't really talked about in this class. Then at the very end, we multiply that by the occlusion. All right, so that indirect light is attenuated by the ambient occlusion factor. That's a lot of stuff. Okay, so that's that stuff in the base pass for the diffuse. What about this UnityGI underscore indirect specular for the specular? Okay, so all of the stuff here involves looking up things in cube maps. So that has to do with our reflection probes. And at the very end, we multiply it by the ambient occlusion map. Oh, I should say it may be the ambient occlusion map, or that may be modulated by that slider. And all of that was to create this global illumination information that is going into Unity BRDF PBS, along with a bunch of other stuff. And this looks like where the actual final physically based shading is taking place. Well, not yet. Unity BRDF PBS, which is in Unity PBS lighting, is itself a bunch of if-thens that choose between a bunch of BRDF functions. Let's see, those BRDFs are in Unity Standard BRDF. And let's see, BRDF 3 is old school, not microfacet based, modified normalized blend Phong. Implementation uses lookup texture for performance. I bet you that is not the one that's standardly used. What about BRDF 2? So this one is a minimalist Cook-Torrance BRDF. It says implementation is slightly different from original derivation. Let's check out this website. All right, so this is an article called the Blend Phong Normalization Zoo. I've seen this article before. It's excellent. All right, so let's scroll down a bit. And, here we go. Minimalist Cook-Torrance. So you can check this out and see what's implemented in Unity. Although the actual comments here say it's slightly different than that, but it looks like that website was the inspiration for this. So let's check out BRDF 1. All right, here we go. Now we're cooking with gas. Main physically based BRDF derived from Disney work and based on the Torrance Sparrow macrofacet model. Here we go. Okay, so depending on whether Unity_BRDF_GGX is set, it uses normalized blend Phong or GGX. If I remember from one of the config files, it's set to use GGX. Smith for visibility term, Schlick approximation for Fresnel. All right, let's take a look here. Oh, this is interesting. There's a comment here. But first, smoothness to perceptual roughness is 1 minus smoothness. Okay, so we take 1 minus smoothness to get our perceptual roughness. We get the half vector, which is the normalized average of the light and the view vectors. But we don't just normalize it. We Unity_safe normalize it. So what is Unity_safe normalize? Why are we doing this? Okay, so we're taking a dot product, but we don't let that dot product get too small. Oh, it's avoiding a divide by 0 issue. So if the result of the dot product is too small, then it clamps here, so we don't wind up dividing by 0. Okay, and here we're going to compute n.v, but there's this lengthy comment. n.v should not be negative for visible pixels, but it can happen due to perspective projection and normal mapping. In this case, the normal should be modified to become valid, i.e. facing camera, and not cause weird artifacts. But this operation adds a few ALU, and users may not want it. Alternative is to simply take the absolute value of n.v. Less correct, but works too. I've never thought about this issue before. I'm pretty sure I don't want to have to think about this issue now. Anyway, let's keep going. Following define allow to control this. Set it to 0 if ALU is critical on your platform. This correction is interesting for GGX with Smith's joint visibility function because artifacts are more visible in this case due to a highlight edge of rough surface. Edit. Disable this code by default for now, as it is not compatible with two-sided lighting used in SpeedTree. So whatever this is doing, it looks like they default to having this be off. Really? Okay, because of SpeedTree or something. If we did do it, what would we be doing here? Besides taking the absolute value, we would be shifting something by a certain amount and then saturating it. Okay, let's pretend it's magic. We just take n.v. All right. And we compute n.l, n.h, l.v, l.h, all the various things we need to do physically based lighting. All right, now we actually have the BRDF. We'll have a specular term, and we'll have a diffuse term. This is usually max 0, n.l, but this is something more complicated. This is a Disney diffuse. Oh, and it includes the roughness. That's unusual. Roughness is usually something we only think about with the Cook-Torrance specular model. So let's check this out. Okay, so the actual diffuse was this Disney diffuse function times n.l. So what is this Disney diffuse function doing? So we're computing something called FD90. That's twice L.H squared times our perceptual roughness plus a half. And that's used in these Fresnel style terms, but this is not a Fresnel effect. The Fresnel effect is part of the Cook-Torrance specular term. This is the function form, but it's being used for something else, including an n.l and an n.v, and then it multiplies those together. So I have seen this before. Let's go look up this at its source. Okay, so here's that highly influential article, Physically Based Shading at Disney by Brent Burley, and let's do a search on the word diffuse. Here we go. As seen in the major data and based on our studio experience, the Lambert diffuse model often looks too dark on the edges, and adding a Fresnel factor to make it more physically plausible only makes it darker. Based on our observations, we developed a novel empirical surface model for diffuse retroreflection that transitions between a diffuse Fresnel shadow for smooth surfaces and an added highlight for rough surfaces. A possible explanation for this effect may be that, for rough surfaces, light enters and exits the sides of microsurface features, causing an increase in refraction at grazing angles. In any event, our artists like it. And it is similar to features we used to have in our ad hoc model, except that it is now more plausible and has a physical basis. In our model, we ignore the index of refraction for the diffuse Fresnel factor and assume no incident diffuse loss. This allows us to directly specify the incident diffuse color. We use the Schlick-Fresnel approximation and modify the grazing retro-reflection response to go to a specific value determined from roughness rather than 0. Our base diffuse model is, oh, this is it. So this is what you see in the code. There's that, twice the roughness, whatever. All right. This produces a diffuse Fresnel shadow that reduces the incident diffuse reflectance by 0.5 at grazing angles for smooth surfaces and increases the response by up to 2.5 for rough surfaces. It was found to be artistically pleasing. Okay, so this is what that is. And if I remember correctly, this is not energy conserving, but Disney likes it anyway. And I guess the Unity folks liked it too. All right, so that's what that is. Okay, and here's the specular term. We will first turn our perceptual roughness into roughness. And how do we do that? Well, we square it. So this is one of those cases where I think it would be clearer just to have this perceptual roughness times perceptual roughness just right here in the code. And here we can choose between a normalized blend Phong or GGX, which is the modern standard. Although I noticed that they clamp the roughness so it doesn't go below 0.002. Let's see. GGX with roughness to 0 would mean no specular at all, using max roughness, 002 here to match HD render loop roughness remapping. I have no idea what that is. Also note the comment here that says, hack. Theoretically, we should divide diffuse term by pi and not multiply specular term, but that will make the shader look significantly darker than legacy ones. And 2, on the engine side, non-important lights have to be divided by pi 2 in cases when they are injected into ambient SH. So basically, this business with pi is always confusing. All right, so let me scroll down. And here's our final specular term where we multiply the visualization term times the distribution term. We're also multiplying by pi. That refers to the comment we just talked about. Actually, it's not the complete Cook-Torrance because there's no Fresnel factor here. That probably comes later. Some nonsense about gamma. Gamma is bad, so I'm going to ignore that. So here we take the specular term. It's the Cook-Torrance, but it doesn't have the Fresnel yet, and we multiply it by n.l. So this is the Lambertian term. Remember that your actual specular color is going to be a Lambertian n.l times your Cook-Torrance BRDF. So this is where they do the multiply by n.l. There's an option to actually just turn off specular highlights altogether. And then there's something about surface reduction. What is this? I've not heard of this before. So let's come back to this. All right, to provide true Lambert lighting, we need to be able to kill specular completely. Okay, this is an option of killing specular completely, I guess. There's a grazing term, which is smoothness plus 1 minus reflectivity. Oh, this is very odd. What is this grazing term? All right, so what is the final answer? So we have our diffuse color times the color of the light times our Disney diffuse. And then we're going to add to that the diffuse from the global illumination, either from the light maps or from the spherical harmonics. All right. Then we're going to add to that our specular term, and that was pi times the visualization terms times the distribution term times n.l. And here we're multiplying by that Fresnel term. So here we are actually multiplying by the Fresnel factor, and then we're multiplying that by the light. And then in the last term here, we add in the specular aspect of the global illumination. So that's coming from the cube map. And that's where this surface reduction thing comes into play. And the Fresnel factor for that is coming from something that includes this grazing term. So this is interesting. I'm not familiar with what this is doing. So the surface reduction is apparently something you get from integrating over the region where n.L is non-zero, n.h times the distribution function, and you integrate over h. And that apparently gives you 1 over roughness squared plus 1. And then for some reason, this 1 over roughness squared plus 1 is something you want to multiply your cube map by. I don't get that. Okay, so let's look up FresnelTerm. Is this in this file? Yes, it is. Okay, 1 minus an angle to the 5th power. Okay, so this is a standard FresnelTerm calculation. Now we have the FresnelLerp. This is a little bit weirder. So this one here is basically lerping between F0 and 1. Here we're going to lerp between F0 and this F90, where F90 is this grazing term. So if we did a standard Fresnel function here, it would be going from spec color to 1, but now it's going from spec color to grazing term. Whatever this is, this feels very ad hoc to me. I've not seen something like this before. I don't understand it. The one thing that I do want to point out that I don't necessarily understand, but it's standard to do, is the Fresnel term you use for something like a standard light source, you use L.H. The Fresnel term that you use for something involving your cube map in image-based lighting, you use N.V. That's just what people do. Okay, before leaving this function, I want to drill down a little bit on what 1 minus reflectivity is. That appears to be set by this fragmentSetup macro, so let's check that out. So fragmentSetup creates a structure called fragmentCommonData. Let's see, here's the sort of stuff you'll see in fragmentCommonData, and in order to fill that out, the macro that is the capital fragment underscore capital setup calls a function, in camel case, fragmentSetup. How creative. All right, there's a bunch of stuff here. I bet you a lot of stuff is happening in Unity Setup BRDF input. All right, Unity Setup BRDF input is actually just a macro that points to the function SpecularSetup, and that function is here. So it looks like this is going to do some texture lookups to get the SpecularGloss, Albedo. Let's check those out. Okay, this looks like it will get specular colors and smoothnesses based on probably various settings that you have in the inspector. I should mention this SpecularGloss function is in Unity standard input, and let's look up that Albedo function. All right, so Albedo, this can get a little complicated if you're using detail masks, but if not, it's basically just a texture lookup. And while I'm here, there's this MetallicGloss function that pulls out various things based on how things are set in the inspector. But I want to know what's up with this 1 minus reflectivity. Let's see on the next line. Oh, energy conservation between diffuse and specular has an output parameter. That's what's setting 1 minus reflectivity. All right, so let's check out this, and maybe we'll be at the bottom of the pile of turtles finally. Okay, so the 1 minus reflectivity is 1 minus specular strength of the spec color. So what's specular strength? Oh, so it looks like it's the maximum of the red, the green, and the blue in the specular? This feels extremely ad hoc to me. Anyway, so if you want to conserve energy, you return the albedo times 1 minus the reflectivity. But that's if you want to do it in a monochrome way. If you want to do it in a colorful way, you take the albedo and you multiply it by 1 minus the specular color. Oh, okay. I see what they're doing. They're trying to balance the diffuse and specular aspects. Interesting. Or you have the option of not conserving the energy and it just spits back the albedo. And I feel like I missed something along the line because there's also things here like 1 minus reflectivity from metallic, diffuse and specular from metallic, but I'm not sure what refers to these. Oh, and I should mention that these functions are in Unity standard utils. Okay, I think we can pop the stack all the way back up to this fragForwardBaseInternal. The only thing we have to talk about here is the fog, but I'm getting tired of talking about this. So it does something with fog, and then it gives you the output. Fantastic. All of that was for the base pass. Let's take a look at the add internal pass. So it looks pretty similar. We have something here, it's additive light. So that's extracting light parameters. And the rest of this is pretty much the same as for the base pass, except there's this thing called zero indirect that, as we can probably guess, creates a zero indirect light because this is for the additive pass and all the indirect light stuff happens in the base pass. And we do this BRDF, fog, etc., etc. So this is just basically a simplified version of what we saw in the base pass. So all of that was just for the forward pass and the additive pass. There's also code we could look at for shadows and for the meta pass that's only used by the global illumination system that's not run real time during your game. And there's also information in here about the deferred pass, but we haven't talked about deferred rendering yet anyway. So I'm not going to go through the other passes now because I'm actually completely exhausted and brain fried from looking at this code. I'm going to take this code here, which is basically Unity standard shader where I've changed everything to my, and package that up as a Unity package. So if somebody does want to create their own version of the standard shader, they can do that here. I think the main place to look if you're trying to make a modified version would be the BRDF functions in the Unity standard BRDF file. My overall impression of this code is that it's a mess. This is clearly something that has evolved over many, many years. I think there's parts of code in here that aren't actually called by any other parts of code in the standard shader itself, but they probably need to leave them around in case there's assets on the Unity asset store that depend on those functions. Things are spread out among a bunch of different files with no real coherent vision as to what goes in what file. It's really pretty painful. And that was for the full version of those shaders. We didn't even talk about the forward base simple and forward add simple and all of that from the simple version of the shaders. If I were to dig into this more, I would probably start by stripping out all of the simple stuff. Just get rid of this altogether. I would get rid of any code that involves shader model 2.0 or below. It's 2022. You can assume pretty much that anything that you'll want to write a game on has shader model 3 or above support. And I'll probably try to take some of the macros and start just substituting them back into the main code just to make it easier to follow what's going on so you don't have to jump from file to file to file looking through macros.